The powerful and amazing capacitor. What is it and what does it do? Well, you can think of a capacitor as a battery. While they work in different ways, both of their jobs is to store electrical energy. A battery produces electrons on one terminal and absorbs electrons on the other terminal. A capacitor doesn't make new electrons, it only stores them. If you look inside of a capacitor, you would find terminals that connect to two metal plates that are separated by a non-conductive substance, or what's called a dielectric. You can actually make your very own super basic capacitor with two pieces of aluminum foil and a strip of paper. It's not going to do the job very well, but it will work. In theory, the dielectric can be any non-conductive substance, but for practical applications, there is specific material used that makes a capacitor work as intended. Mica, ceramic, cellulose, porcelain, mylar, Teflon, and even air are some of the non-conductive materials used. The dielectric dictates what kind of capacitor it is and for what it is best suited. Now, depending on the size and type of dielectric, some capacitors are better for high-frequency uses, while some are better for high-voltage applications. Capacitors can be manufactured to serve any purpose, from the smallest plastic capacitor in your calculator to an ultracapacitor that can power a commuter bus. In fact, NASA used glass capacitors in the space shuttle circuitry and to help deploy space probes. Some of the different types of capacitors are air, often used in radio tuning circuits, mylar, which is the most common for timer circuits, like clocks, counters, and alarms, ceramic, used in high-frequency applications like antennas, X-ray, and MRI machines. For electric and hybrid cars, supercapacitors are used. In an electronic circuit, a capacitor is represented with this symbol. If you connect a capacitor to a battery, the plate on the capacitor that attaches to the negative terminal accepts electrons that the battery is producing. The plate that attaches to the positive terminal of the battery loses electrons to the battery. Once it's fully charged, the capacitor has the same voltage as the battery. Now in this case, it's 1.5 volts. For a small capacitor, the capacity is small, but large capacitors can hold quite a bit of charge. There are capacitors as large as soda cans that can hold enough charge to light a flashlight bulb for over a minute. You can compare a capacitor to nature in the form of lightning. Now think of one plate as the cloud and the other plate is the ground, and the lightning is the charge releasing between these two plates. Obviously, in a capacitor that large, you can hold a huge amount of charge. Let's say you hook up a capacitor like this. Now here you have a battery, a light bulb, and a capacitor. If the capacitor is pretty big, what you will notice is that when you connect the battery, the light bulb will light up as current flows from the battery to the capacitor to charge it up. The bulb will get progressively dimmer and finally go out once the capacitor reaches its capacity. If you then remove the battery and replace it with a wire, current will flow from one plate of the capacitor to the other. The bulb will light initially and then dim as the capacitor discharges until it is completely out. A capacitor's storage potential, or capacitance, is measured in units called farads. A 1 farad capacitor would be pretty large, as big as a 1-liter soda bottle. Now, most capacitors that are used in electronics projects are measured in microfarads, or millionths of a farad, shown as this. The difference between a capacitor and a battery is that a capacitor can dump its entire charge in a tiny fraction of a second, where a battery would take a number of minutes to completely discharge. Now, I'm sure you've seen an electronic flash on a camera. Well, that flash is generated by a capacitor. The battery charges up the flash's capacitor over several seconds, and then the capacitor dumps the full charge into the flash tube almost instantly. This can make a large charged capacitor very dangerous. Flash units and TVs have warnings about opening them up for this reason. They contain big capacitors that can potentially kill you with the charge they contain. The Leyden jar is one of the first devices invented that is basically a capacitor. It consisted of a glass jar, half filled with water, and then lined inside and out with metal foil. The glass acted as the dielectric, although it was thought for a time that water was the key ingredient. There was usually a metal wire or chain driven through a cork in the top of the jar. The chain was then hooked to something that would deliver a charge, most likely a hand-cranked static generator. Once delivered, the jar would hold two equal but opposite charges in equilibrium until they were connected with a wire, producing a slight spark or shock. Benjamin Franklin also worked with the Leyden jar in some of his experiments with electricity, and he found that a flat piece of glass worked as well as the jar model. prompting him to develop the flat capacitor, or what was called the Franklin square. Now, remember the farad? Well, years later, English chemist Michael Faraday would pioneer the first practical applications for the capacitor in trying to store unused electrons from his experiments. This led to the first usable capacitor made from large oil barrels. Faraday's progress with capacitors is significant because his work is what eventually allowed us to deliver electric power over great distances, and we ended up using his name, farad, as a measure of capacitance. So there you have it, the powerful and amazing capacitor. If you missed any of my other KIPK tips, click the end cards on the screen to check those videos out. More KIPK tips next week. Thanks for watching.